Saga. Okay, so here's our practice problem for pitch circular motion, and this is a hanging object, kind of like the pig that we saw. And here we go. This is a 6.5 E4 T.1. In an effort to assert your playground dominance, a kindergartner has challenged you to a game of tetherball. And you decide to make your physics overlord proud and inspire this young lad to study harder by destroying them in this playground game using sophisticated calculations. So we're playing a small child in tetherball, and if you've never played tetherball, it's just a ball hanging from a pole, and you knock the ball around, and you just try to wrap, and whenever the ball hits the pole, you're the winner. Napoleon Dynamite plays it, and if you've ever seen that movie. What we do know is if we start this problem now, to show the sophisticated calculations that we're capable of, we know that the ball's making a 59.5 degree angle from the vertical pole. So this angle here is 59.5. So we know theta equals 59.5 degrees. And it is 1.5 meters from the pole itself. So we know that the radius of the circle that the ball is making is 1.5 meters. Okay. Previously, when we did our Sokotoa practice, we would have just tried to figure out the height that the ball is at. But let's take it a little further. What amount of tension? Okay, so we're looking for a tension here. Does the 0.5 kilogram ball, so that's a mass, so we know the mass is 0.5 kilograms, exert on the rope if it's moving at a speed of 5 meters per second. So that's our speed here. Velocity equals 5 meters per second. So let's take a look at this. And our rope is weightless here. We're not doing anything weird like that. Well, there's actually a few ways we could solve this problem. If we're just looking for a tension, we consider the free body diagram. Here's our tether ball. There is a tension pulling it up and to the right, and there is a weight acting on it straight down. If we wanted to, we've already seen this, we could, break this tension that we have up into our two components. We can say, look, this is a vertical component, Ty, which has to equal the weight. Or we could say, hey, look, this is some Tx, which is the centripetal force. So you actually have two ways out of this problem, which is actually pretty cool. You could say Ty, which if we recall, Ty is T cosine of theta, and Tx is T sine of theta. If you don't know where we got those, check out the prior videos we've done on pitch circular motion. So we could just say this. We could say that these vertical forces have to be the same. We could say the top is positive, down is negative, and say that T cosine of theta minus the weight, which is mg, equals 0. And we could solve for tension here. Or if you're like, wait, but I really like using centripetal forces. Sure, we could do that too. We could say that centripetal forces, that T sine theta equals the centripetal force ma, which is really mv squared over r in this problem. So it actually doesn't matter which one you use here. We should work out to be the exact same thing. If we solve this for tension above, we'll add mg over and then divide by cosine. We see that tension equals mg over the cosine of theta, which equals 0.5 times 9.8 divided by the cosine of 59.5. Let's see what we get here. So half of 9.8 is 4.9. Divide by the cosine of 59.5. We get a tension of 9.65 newtons. If we go down below and solve this for tension here, we just have to divide by the sine of theta in this case on each side to find that tension. So we quickly see that our tension will equal mv squared over r sine theta. And if we put in our numbers here, that's 0.5 times our velocity, which is 5 squared, so it's going to become 25 in a second, divided by 1.5 and the sine of 59.5. If we put all that together, what do we get here? So 0.5 times 5 squared of 25. So 12.5 divided by 1.5 is 8.3333333333. Whoops. Divided by 59 point, the sine of 55.5, 59.5, and we get 9.67. So I probably rounded somewhere a little bit. Those values are the same values. I think I had a little bit of a rounding error somewhere in here. But we see that no matter which equation we'd like to use, we can use centripetal motion or statics, knowing that our motion is up and down, to figure out what the tension is of this rope. So a pretty cool thing in this problem. Maybe this problem would have been a little bit harder if the mass wasn't given to us. In which case, what would we have to do in order to solve that? Would it be solvable? I don't know. Just kind of spitballing here. But we've seen problems like this now. Hopefully, we're getting a really good feel on them. We know that this tension is the component, or it's the force vector that's broken up into its components, and with that, we can solve a lot of this stuff out. Okay, so with that, this problem is indeed finished. No matter which way you took it, you got the same answer because the tension must be the same. And I hope it worked out for you. Our last example problem, our last practice problem that we'll see for this pitched circular motion will be a car going around a bend. We are going to make it a little bit less complicated than they can be, but check out that video for our next one. But until then, adios and take it easy.